Good afternoon, everyone. Okay, so welcome to our first tutorial. Okay, for CG1112. Okay, I sent you all the link just now. So we'll use the same Zoom link for all the tutorial sessions. Okay. So if you look back at our schedule, it is we will be finishing everything by week 9, week 10. All right, and then our final assessment is also earlier. Okay, so the whole idea is to finish up all the stuff earlier so that you can focus on the project for the remaining of the weeks that we have. Okay, and this is also done with uh, intentionally because of uh, as a contingency in case things go south with COVID. All right. Last year, when we were running this module, it was a very stressful time for all of us, the students and for the lecturers, because every week things were changing, and we didn't know if we would survive till the end of the semester. All right, and unfortunately, we did not. Okay, and we went into lockdown before that. So the students uh, didn't sort of complete all that we wanted them to complete, and the assessment also couldn't be done uh, properly, correct? So we just had to do some online assessment, make them create videos and submit the reports and things like that. So uh, the students had a tough time, especially because of the situation when you don't have access to the lab and we can't meet you all anymore, and when components have issues, we can't help you as well, correct? As long as you're coming to the labs, we can still swap out components, troubleshoot, and fix up things, okay? But when we can't meet and then suddenly things go wrong, it's really everybody is stuck, okay? We can't do it. So we hope not to have a repeat of that. And the situation is still, I wouldn't say very much in a safe zone yet, correct? Because there is still, if you look at the news, there is still community spread, and there is still some talk about additional measures being potentially being imposed and things like that. Okay, so let's just hope for the best. Okay, so that is one of the reasons why we push everything forward. Okay, so that you can get everything up and running quickly, and hopefully nothing else happen, and we can still go through till the end and have a proper assessment. Okay. So in terms of tutorials, every week we have tutorial. If you look at the schedule, the weeks where you may have the midterm the week after, or the Saturday just after tutorial, we will release the solutions in advance. Okay, so that you have a chance to go through and get prepared. Okay, while you're also preparing for the midterm or final assessment the day after. Okay, so let's get started. So today's tutorial is fairly easy. Just a recap of the things we have done so far in terms of the RPI, the Git, and algorithms. All right, and then after we're done, I will talk about some other things that will put things in perspective. All right, why this module, and why some of the things you're going to be learning is important for you all as computer engineers. All right, so let me start with the material first. Okay. Okay, so these slides we will, I mean, all the solutions and slides I will send to you all later on. And usually what I do for all my classes is all these recordings I will also upload, and I'll send you all the links. Okay, so anytime you want to refer back, you can look at those videos that I upload. All right, and as a revision. All right, so the first question is basically comparing your laptop or desktop against the RPI. Okay, so I don't have an RPI here with me. I only have Arduino here. RPI is in the office. But basically, the RPI, as you have seen, is quite a powerful system, all right, where you are actually capable of running full desktop kind of environment on it. Correct. So you can see that it's very capable. All right. Powerful. And you have also used the Arduino Uno, correct, in your CG1111. And comparatively, definitely, you can say that RPi is definitely a lot more powerful. Okay, so but when you compare it against a laptop, okay, that you're using on a desktop, how would you compare some of these areas that we talk about in terms of power, hardware, and so on? Okay, so if you of course here we did not specify anything, so you just take any example laptop. Okay, so in this case what you have taken is a old MacBook Pro against this RPi 3 model B plus. Okay, and what you see is in terms of voltages and current. Okay, so in terms of power requirements, definitely this is much higher. Correct, your laptop is much higher compared to your RPi. So that itself gives you an indication of when you will use laptop compared to RPi, because for a laptop to be running, you definitely need to be connected to a main supply if you want to continuously be running it for the whole day or something like that. For RPi, if you are able to connect to a power bank, you can potentially run it for many hours, okay, with just a small power bank connected, okay, depending on how you write the code and how you do power management. Processing power, definitely a desktop system or laptop system is going to be having a lot more processing power as well as memory. All right, so in terms of memory requirements or memory availability, your laptop is a lot higher because generally you are using it for a lot of concurrent applications at the same time. Okay, even though the RPi, we used it as a sort of desktop in the studio. Generally, you use it in that form just to give you the environment to develop your application or develop your code. In most cases, this kind of bots, you use it for a particular embedded solution. All right, so you probably only need enough memory to store your application code. All right, so that is why you don't need so much of memory. But in many of these devices, you also have some capability of extending memory. So in your laptop, of course, you have SSD, hard disk drive, and so on. In our ARPA, you have SD card. Okay, so if, for example, you are in our application, which is a search and rescue robot. Okay, if let's say we want you to keep track of all your movements and what is happening, how you're moving around, and so on, then you need to store it somewhere. All right, and then you need to be able to retrieve it. Okay, of course, if you have enough memory or RAM, you can do it. If you want to keep it safe, you probably want to write to SD card. Okay, um, in the very first batch of I mean, whenever we have a new module, it's always the first batch who are guinea pigs, right? In a sense, because we are also figuring things out. Students are also figuring it out. Okay, so in the very first batch of students who did this module, in the final assessment, we actually asked them to do a backtrack. Okay, that means after you do the search and rescue operation, you must be able to backtrack all the way to the starting point. Okay, but after that, we realized it is too challenging. All right, and then we remove that element after that, and then that is where we came up with some other aspect of the challenge, and we said, okay, we introduce this color detection. Okay, so we put some colored objects along the way, and you must be able to detect and correctly decode the color. Okay, but of course, if let's say in a real life scenario, you want to keep track of your location in a secure or a permanent storage, and the SD card is one option for you. In terms of ports, actually the Raspberry Pi also is very well equipped. Okay, that is quite comparable to what you get on most laptops as well. Okay, in terms of operating system, you also have a full-fledged OS. All right, that can do just about everything. Correct, as what you saw in the studio, you can run your web browser, you can play music. Okay, you can do anything. A lot of things very similar to what you can do on your computer. Okay, so technically they are very similar, The main, I would say, difference is that the fact that RPi can still be a lot more portable and a lot more better in terms of power consumption. So it's a portable embedded device where you use the RPi for. Whereas a laptop is still something where you need a full uh, fixed power supply to be constantly enabling the device. Okay, so that is a comparison between RPi and a laptop. Now, this is not in your question, but if you compare, let's say, the RPi and the Uno, all right, so the Uno is basically something you know, okay, from your experience with CG1111, okay. So if you compare the two, what do you get? So the RPi runs on 5 volts, okay, that part is fine, and consumes about 800 milliamps, okay. Again, this is just a bare board. The Arduino Uno, on the other hand, consumes a lot less current. So in terms of power consumption, definitely it is much lower. Uh, and in terms of voltages, you can operate at 5 volts or you can also operate at 3.3 volts. Okay. Uh, so you have to remember that most embedded boards, you may apply a power based on the actual board that you're working with, but the controller that you are actually sort of writing the software for may be able to run at some other voltage as well. Okay, so when you strip out everything and you just look at it at the microcontroller level, then you can just say that, okay, I just want to use the ATmega 328 and I can run at 3.3 volt. Okay, in terms of the processor, again, like what we saw, ARPA is very much more capable. The 8328 that we are going to be learning more about is a very simple 8-bit controller. Okay, again, much lower speed, much lower storage space, and so on. But again, the idea is quite different. Right? The application, the use case is very different because in the Arduino Uno, you are writing software for a very specific application that is going to have limited, or you already know that it's an application with that requires limited processing power. Okay, so you don't need such a advanced system. Okay, most of the I/O pins, like what you've used before in CG1111, is things like your GPIO, your A to D converter, your PWM, and things like that. So you will be using the same things in this module as well. Then, of course, your full-fledged computer as an OS, you will see in RPi. Your microcontroller can only run one task. Okay. Okay. So let me come here. Okay. So in one task, as we say, is because if you recall what you've been doing in CG1111, you write a main loop, okay, and then you may have a lot of functions that you call, and the only other thing that is not in sync with that loop and the function is your interrupt. Okay, but of course this will change. Okay, once you learn about multi-threading, okay, which you will learn in year 2, okay, in another module that I teach. But actually, we are also going to be introducing you to multi-threading in this module as well. Only thing, you're not going to be doing any particular multi-threading coding, okay, but the RPi will run multiple threads together. Okay, we will see that later on when we establish the connection. Okay, so in one of the studios, we will establish a connection, that means RPi. Okay, RPi will talk to your Uno, okay, through serial interface. Okay, and this serial interface communication, you will see that your RPi will actually be multi-threading. Okay, but again, we will not focus on it too much because that is not the aim of this module, but I will show you what is happening when we come to that studio. Okay, so that is basically just to give you some overview of the hardware that you are dealing with. All right, and so you have an idea of when or what is the use case for these different types of hardware that we have. Okay, let's look at the algorithm. Okay, so in this question, basically, if you look at this objective, you want to sum up 100, the first 100 integers. All right. Now, how do you come up with the algorithm, and how do you compute the time complexity of your chosen method? So in this case, you take the addition to take a constant time of order 1, And if we double the problem size, does it take more time? Okay, so let's look at it from a possible solution. Again, this is not the only way. You may have different ways of doing it, but what we can do is we can initialize a counter and a total variable. Okay, so as we go through the loop, we add to total, okay, and then we keep incrementing the count. So basically what you have is two additions over here. Okay, two addition operations each time you go through the loop. Okay, so in total you take 2 to the power of n minus 1 additions, and each addition we say it is order of 1. All right, that means effectively the total order is order of n. Okay, if you remember from a studio, we don't factor in any constant in the final order representation. Okay, so the 2n we don't put, the minus 2 we don't put, we just take it as the uh, representation that is more generic, okay, towards the algorithm that we choose. Okay, so since the order is order n, we say it is linear. That means as n increases, you will linearly increase the time that you take. Okay, so if I double the n, okay, that means if I add on more variables to add on, then the time will also increase by that same linear amount. Okay, so that is basically giving you the idea of how you say, how you come up with the algorithm, and you are able to give a justification on the order of this algorithm. Now, here is another example. Okay, so this is basically this student, okay, who was asked by his teacher to find the sum of integers from 1 to 100. Okay, so normally for most of us, if we don't think or we're not sure how to simplify anything, what we will do, we might just carry on, right? 1, 2, 3, and so on. But what this student did was he saw that if you take the first number and the last number, right? If you take 1 and 100, you add up, you get the same value, 101. If you take one more and one less, you add up, you get the same. All right, so he saw that if I go in this direction and I add up all the numbers, I'll always get the same results, which is 101. All right, so all he had to do was uh, he could see that every time I add up, I get 101 as the result, and there are 50 such pairs that I will get. Correct. So instead of adding up everything, you could straight away calculate this and get the answer. Okay, so right now the same thing, what would be the order? Okay, so if you look at it, basically all you need to do is you only need to do the addition once. Okay, and calculate the n by 2 once. All right, because you only need to compute these two things. Okay, and the multiplication once here. So since you only do this once, okay, and also the multiplication only once, the order is always the same, is a constant time. All right, so even if the size increases, all right, the amount of time you take will still be the same. So this is the same problem, but now you are able to say that the order of your algorithm is now constant regardless of the size. Okay, again, all of this plays a part because especially when you're talking about real-time response of a system, uh, the way in which you are able to write an algorithm that can compute faster can make a lot of difference, right, in how far the system is able to respond. Okay, so these are things that you need to look at in terms of complexity, and we are introducing this to you, but definitely you are going to be learning more later on. Okay, so is there a difference between time complexity and growth term? Okay, time complexity is basically the we look at it in terms of the time the order of the function in terms of the time that it takes. Okay, growth term, I'm not sure if is referring to the size. Okay, then it is about how you use memory will relates to the algorithm. Okay, so when you talk about algorithm, there's two parts. There's time and then there is the size or the memory. All right, so there's two different parts to it that we need to weigh. Okay, so actually we're going to be discussing this in a while in the next question. Okay, so I'll come to that again in a while. Okay, so now let me come back here first to discuss some of the questions that we saw earlier on. So these are the work functions that we gave you in the studio. All right, so in this first question here, you can see that unit work is independent of n, correct? So regardless of what is the n value, I always run the loop up to 567. So it is always constant time. So the order is 1. Okay, that means always the same amount of time. B is basically n, because whatever n I pass in is coming in over here. So as what we saw, any constant in front of the n, we generalize it. So we can remove it and we just put it as order n over here. Okay, so the constants we can remove from the expression. Okay, for work C is basically a nested loop. Okay, so it is n into n. All right, so that is why you get n square, and whatever constant that you have here, you will remove as well. So again, you generalize it to say it's n square. All right. So in many cases, as much as possible, if uh, we may initially start off with writing code to focus on the functionality first, all right, because that is the initial objective. And after we get the functionality working, then you can work towards seeing whether any part of it can be improved. Okay, for this module, like I said, this idea of complexity, we're just introducing it to you. You don't actually need to worry about this too much in your project or so on, because like I said, the project itself, the framework, the architecture, the device drivers, a lot of the things will be given to you. Okay, the things that we develop along the way, you will add on, all right, and then you will be able to sort of put things together. All right, so the complexity part, you do not need to worry about applying it too much in this module, but it's good to know this concept and you will revisit them later again. Okay, work E is basically what we saw here, where we say that we are taking a particular unit work, and inside that work function, you call recursively yourself divided by 2. Okay, so if I pass in work n, I call n by 2, then I call n by 4, and so on until I hit n equals to 0. Okay, so if I were to, for example, give you n equals to 8, okay, so what will happen? Okay, so let me show you here. So 8, when I initially call this function, I will call myself with 4, then 2, then 1, then 0, correct? So for 8, all right, you have 1 unit of work, and 0, you have 1 unit of work. And every time I call myself divided by 2 is 1 unit of work. So basically what I need to do is to find out this particular part, how many elements are there. All right, and that is actually given by the floor of log to the base 2 of n. All right, so if I do a log to the base 2 of 8, all right, I will get 3, and 3 plus 2. So this 2 here is referring to the starting one and the ending one. Okay, so this 2 will always be there because you have the starting point and ending point. And the log to the base 2n is giving you the number of iterations that you will call when you continuously call yourself with dividing by 2 each time. Okay, again, since we always generalize it, okay, we can simplify this expression and put it as order log to the base 2n over here. Okay, so I think most of you in the studio itself saw this and were able to figure it out, or discussed with the TAs and also saw how this thing works, which is good. Okay, so this is exactly what you saw in your studio. Now for work D, okay, basically work D, what is happening is you are actually calling yourself twice, okay, with the same divide by 2. So n will be n by 2, n by 2, and then n by 4, and so on. Okay, so let me show you the next picture over here. So if I were to have 16, then you can see that every time I call myself, again divide by 2, and what is happening is in each iteration I have n units of work, okay, which is the same n, which is 16 in this case. So I start with 16, but in each level I also have 16 units of work, okay, because over here I do the for loop here where I do n units of work each time. All right, so effectively what is happening is in each layer or each level you are doing the same number of units of work. All right, so it is the same thing, log to the base 2 16 plus 2. Okay, so this 4 here is again obtained through the log to the base 2 of the n, and the 2 here is the starting and the beginning. All right, this is the number of layers that you have, but in each layer you're also doing n units of work. All right, so that is why the final expression is given as n log to the base 2 n. Okay, because in each layer, so you have log to the base 2 n layers, okay, or levels in this tree, but in each level you also do the same amount of work, which is n units of work. Okay, so that's why you get n log to the base 2 n for the total complexity in this question here. All right, so again, this is exactly what you saw in your studio. So when you were doing it and you're plotting the curves, you also would have seen something similar. All right. Okay, so this is basically the time and space complexity, like what I mentioned just now. All right. Now, in terms of time and space complexity, these are two uh, sort of always contradictory requirements that you are always trying to balance in the system. Okay, because you want it to be fast, but at the same time, you want it to occupy as little memory as possible. Okay, and this is basically the challenge that almost all embedded systems are facing, correct? Because you're always talking about systems with limited amount of memory and processing power and so on. So you want to squeeze a lot of stuff inside, okay, in terms of the space, but at the same time, you want it to be as fast as possible. All right. So in this example, we are given this character of a string of n characters, and we want to tally the frequency of occurrence for each character. Okay, so you have A. Okay, so in this string you have A, B, exclamation mark, and so on. And as you can see, A appears 2 times. Okay, B appears 1 time, and so on. All right. So we want this result. We want this output over here. Okay, so we are asking you to propose 2 algorithms. Okay, one is you do not store any prior tally. That means every time you go through all the characters and you calculate, okay, for each time, for each character in the string. The other one is you use some additional memory to store what you already counted before, okay, and then you reach the final answer. Okay, so these are the 2 different algorithms that you are asked to think about. So let's look at 2 possible answers. Okay, so one is in algorithm A, where I go through the loop. Okay, so in terms of the loop, there is an outer loop over here and an inner loop. Okay, for the outer loop, I will look at the string. So I have a string, correct? Then I take the one character, okay, the current character in the string, and then I try to check whether it matches any of the other characters, okay, in the string as well. And then I will be able to print out, okay, if the current is the same as string I. Okay, so there's one outer loop and then there's one inner loop that goes through all the other elements in the string, and then I go through and repeat again and again. So in terms of time complexity, you have a nested loop. Okay, so you have order of n squared. In terms of space complexity, you only is fixed as order 1. So the amount of space you use in this algorithm is fixed because you only have I, J, frequency, current, and so on. So this is independent of n. Okay, so you doesn't matter how big n is. Okay, how big the string is, you will always have the same amount of a fixed amount of space you need to run this particular algorithm. Okay, now let's try the other approach. Okay, the other approach, basically what is happening is, okay, you are trying to keep some information earlier on, okay, or what you have already calculated by using additional memory space, all right, and then you see whether you can save on the time. So in this case, what we are doing is we are creating an array of 256, okay, initialized to all zeros. Okay, so the reason why we have this array of 256 is actually uh, to reference the characters based on the ASCII string or ASCII representation. Okay, every character that you have on your keyboard is actually represented by ASCII code. Actually, it is only 7-bit code. Okay, but in most cases, 7-bit is not compatible. So usually, what we do is we just sort of round it up to 8-bit. Okay, to make it easier to store this information somewhere. Right? If not, the 8-bit is just there, but then you're not using it. Okay, so this array that we are using is basically to reference the ASCII value of each of the characters. Okay, so don't worry about ASCII so much. We will actually be again seeing this ASCII representation later on. Okay, but if you know, basically every character that you type on your keyboard is actually there's ASCII code for it. So that is how your computer is able to interpret what is a uppercase A, what is a lowercase c, and so on. Okay, in this algorithm here, what is happening is we are saying that for I equals 0 to n minus 1, we are going to go through this entire string. And what we want to do is we take the string I and we plus plus. So initially, we have all of it initialized to 0, correct? So all of it initialized to 0. Okay, so let's assume that this point, this space here is representing A. Okay, and this one is representing B and so on. Okay, ASCII A, ASCII B. So string I, so when I is 0, let's say the first character here is A, so what is the A, B, okay. So it's A, B, exclamation mark something. So when string I is represented by character A, this value will become 1, correct? And then B, then this one will also become 1. And the next time what will happen, when I see another A again later on, this one will become 2 and so on. All right, so I'm using the ASCII representation of the alphabet to point to a particular index in the array, and then I just increment that count in this array. Okay, so one loop is basically to get all these numbers, and then the next loop is just to print out. Okay, so in terms of time complexity, the order is n. All right, because you do this n time, you do this n time, so technically it is 2n, but you again you generalize it, so you say it's order n. In terms of space complexity, you are only going to use a fixed amount of space, correct? The I, J, the array, and so on. Okay, so if you look at this algorithm and you look at the earlier algorithm, you can see that the trade-off is what? Here, the biggest thing is, okay, you have occupied significantly a significant amount more memory than the earlier approach. Okay, so there's a question here. In what situation will space complexity depend on time complexity? Okay, so you can't really say that there is a direct dependence. Okay, but what I would say is that they are always contradictory requirements that you are trying to balance. That means whenever you try to increase the amount of when you want to reduce the amount of space that your system is using, there's a high chance you may end up spending a bit more time to finish the computation. All right, and the other way around. Okay, when you try to save on time, you will end up using a bit more space. Okay, so it's always about the balance. So it is not to say that it is directly linked, but in most applications, you will find this conflict happening where time and space are always sort of pulling each other in different directions. Okay, that is where you need to have a balance. Okay, and that is where also other approaches to solve the problem will come in. What do you mean by other approaches? Okay, so instead of using software to do it, can I use hardware to do other things in parallel, say? Okay, so some of you, I don't know whether you already studied the modules or going to study. So there are other ways of implementing uh, solutions. Okay, one way is what we call using FPGA. Okay, I'm not sure. Are you all studying it now? In any module right now? Is anybody? Yes, no? Okay, so if you are not studying it right now, probably you'll be doing it in the next semester. Okay, so in FPGA solutions, basically what it does, it is a way of writing software that translates to hardware, and that allows you to do or perform computations a lot more efficiently uh, that uh, compared to your normal microprocessor or microcontroller based approach. Okay, that is one way. Okay, so I just saw a message that you might be doing it into 2026. Okay, so I'm not too sure, but I know you will definitely be learning this. Okay, then there's also the other approach, like what I mentioned just now, which is multi-threading. Okay, so in multi-threading, you will also be able to achieve some concurrency where code uh, multiple pieces of code can run sort of in parallel, okay, to achieve the objective. So that you will study in 2271. Okay, so that is a year 2 module. All right, so there are other ways to balance this out. Okay, so if your current situation, your current hardware and software solutions cannot fulfill the requirement, okay, either in terms of time or in terms of space, then you need to look at how to uh, sort of upgrade or change your approach to incorporate some of these other techniques and solve the issue. Okay, so again, these are just different ways of solving it. Okay, but for now we will focus on current approach, which is ARPA and Arduino. Along the way, as you're learning other modules, you will slowly see that I can actually put together a lot of different things and solve the problem. Okay. Okay. So in this case, you can definitely say B is the winner in terms of trade-off. All right. Again, I say why is it a trade-off? Because you are willing to sacrifice some space. But right here, if you look at it, it's 1, 2, 3, 4, four variables. Okay, here you have 56, 57, 58, 59, about 260 variables. Okay, so it is about a huge jump in the memory space. Okay, but in terms of overall time, I would say that additional memory is worth it because you save a lot of time. Okay, so that aspect is good. And another thing is also that it is now uh, complexity is only order n compared to here is n squared. All right, so as n increases, the rate at which a is going to increase is going to be a lot higher compared to b. Okay, so that is also another factor you must take in. All right, of course, this is one application where we are dealing with raw data. Okay, in many real world applications, you also want to do what we call pre-processing of data. so that instead of dealing with uh, the whole chunk of data at the same time, you already do some processing. Okay, when you say pre-processing, it could be you already filter the data, you have sampled it, and maybe you have already cut out some parts of the data which you do not need, or you have done some transformation so that the data is now much smaller. Okay, so there's a lot of different things you can do to data before you actually compute it, okay, or do some actual computation to get a result. So that pre-processing, again, you will be learning things like signal pre-processing, like in CG1111, you talked about filtering operation. Okay, so you can do analog filter, you can also do digital filter. All right, then in terms of processing, you can also transform your data from one domain to another domain. So maybe in time domain, it is too much of data, then you do a Fourier transform, you go to frequency domain, and then you looked at some power information from the frequency band information. So in that transformation, maybe the data from maybe 1024 bits can squeeze down to 128 bits. Correct. So there are different kinds of pre-processing techniques you may employ in future to look at the data differently, and that can help you with processing. Okay, so it's very different. Okay, when you talk about you write some MATLAB code or Python script on your laptop to process the data, and everything works fine. All right, but then when you want to translate it to hardware, that same approach cannot, or in most cases might not directly work. Okay, because the hardware in many cases is going to have limited processing and limited memory capabilities. Okay, so what you did on your laptop, your Python script, your MATLAB script, all these things uh, may not be directly transferable. So you need to think of what to do. How do I change my approach or use the correct hardware, software, uh, sort of integrated solution to be able to replicate what I did on my laptop on my embedded platform. Okay, so there's a different way of thinking. Okay, so that was on algorithm. Okay, then we introduce you to Git in the most recent studio. So again, Git is one of the many different software versioning platforms out there, and you will also be learning different variations to Git and other versioning software in different in other modules as well. Okay, so let's look at this scenario. You are working on a solo C coding project. Okay, there is one function X where you have two possible implementations, A and B. All right, so these two possible implementations are quite different because you have different algorithms, different data structures, and so on. All right, and you want to try both of these separately. Okay, right now what would you do? You probably comment. All right, you will have different function names, then you comment your code. Okay, and this time I call function A, then after I call function B, and so on. So these are techniques, yes, we can do right now without using Git or any versioning. Okay, but what would be a better approach to do this? Okay, so one possible way is, okay, you commit your original code first. Okay, and that is without this function, because this function is the one that is going to change between version A and version B. So what you can do is you have a particular commit where you put in function X, and then what you do is after that you can implement your version approach A. So one way of processing this code and processing this data, and then you commit it, and then you put it as this having a particular version 2.0A. And after you do that, you can check out version 1.0. Okay, and then you implement the second approach B and commit as 2.0B. Okay, so now you have two versions to it based on two different commit. Okay, so in Git you can check out a particular commit. All right, so with version 1 as the base version, you now have two other versions, 2.0A and 2.0B. Okay, so as and when you want to use either version, you can do that. Okay, so this is one possible way based on what you already have tried out in the studio. Okay, there are of course alternative approaches which are better, and one of it is branching. We did not go through this in detail, or we did not ask you to try this much in the studio, but you can try it out on your own, where what you can do is you can actually split up or split from your main to separate branches or lines of work, and this can make such approaches where you want to try different things at the same time easier. Okay, again, these are just things for you to try out and explore only, but from what we have taught you so far, you can just do what we have shown you here, where you can put in different commits with different implementations. Okay, the branching and a lot of other functions that Git supports is for you to explore on your own. Again, that is only for your self-learning. Okay, so that brings us to the end of the tutorial here. So again, this is just some simple questions just to get us to review what we have done and what we have covered so far. Okay, so before we end, let me just um, share with you something else. Okay, so next week, like I said, I'll be sending out an announcement in a while, but I've already uploaded all the material for next week's studio. So the first studio is on soldering and wire wrapping. Okay, so those of you who have experience with it, good. You can help your friends and show your friends how to do it. Okay, but at the same time, me and Uncle Jalil and all will be there to help to show you how to go about with this. And besides, okay, in Studio 2, we'll be introducing you to the bare metal programming for the GPIO functionality. Okay, so that will be back to using the Arduino Uno and how to do the bare metal programming. Okay, so before we end, let me just to maybe give you some motivation on some of the things that you can be working on in the future. Okay, so this is something that I just saw today. Let me see. Okay, so I do not know how many of you have taken the or collected your TraceTogether token. Okay, I know some of you may be hesitant, some of you already done it. Okay, but the TraceTogether token is basically an embedded device. Correct? It's already an embedded device which is capable of uh, doing the things that we talked about, correct? In terms of or what we have been told in terms of uh, interconnecting devices together, storing data, transferring data, and these are all things that you actually can do as a computer engineer. All right, even right now, many of you can do what TraceTogether is doing. Okay, so let's have a look at what TraceTogether is about. Okay, so this is actually the technical write-up document. Can you all see the document? Yes, no? Yes, okay, good, thank you. Okay, so this document, you can just Google it, you'll get it, but I will also email you all if you want to have a look. So let's just have a look at this hardware design, okay? So if you look at this hardware design, basically what do you have? You have a BLE system on chip. Okay, so this is basically nothing more than a customized microcontroller. Okay, so when you see system on chip, basically what they are doing is they are taking the microcontroller capabilities, okay, but integrating all the necessary hardware peripherals, everything together, and creating a customized chip for this particular application. Okay, and for this system, as you can see, you have a battery pack here. Okay, lithium battery pack. Okay, you have a crystal, okay, in order to clock the device. So here you have a few different crystals, one at 32 megahertz, okay, one at 32.768 kilohertz here. All right, so here you can see that there's a crystal here to run or clock this RTC, and this RTC also has a separate battery. Okay, anybody want to guess what is RTC? You should know, I think. RTC, what is RTC? Yes, okay. So it is real-time clock. Okay, and this real-time clock is basically a separate hardware that is able to keep track of time regardless of whether the system is powered or not. Just like a laptop, right? Even if you totally shut down your laptop, you plug out the power, everything, okay? And if you even take out the battery at the back of your laptop, okay, and you keep it for a few days and later you plug it back in, you would still show you the correct time and date, okay, because there is a separate small battery pack, okay, and a separate RTC module that is there running in the background all the time, okay, keeping track of your time. Okay, so that is what the RTC is there for. Okay, and you can see that there's a lot of hardware interface that you are familiar with. One is ADC, okay. UART is the serial interface, which we'll be covering again in this module. I2C is another serial interface, which we will not cover in this module, but in other modules. Okay, SPI is a serial peripheral interface, which is another way of communicating with devices, and that is used to communicate with the serial flash. Okay, so the serial flash is probably used to store your code, store all this information from the communication between your TraceTogether token and other tokens nearby. Correct? Okay, and then besides that, you have your antenna, okay, and your monitor for your battery. Okay, so if you look at this hardware block. Okay, so now let's look at some of the specifications that they have given us. Okay, so these are some of the hardware specifications in the document. All right, so LEDs, real-time clock, okay, batteries, okay, Bluetooth, okay, and it is using a 32-bit ARM Cortex M4 device. All right, now why do I want to show you all this is because if you look at all of these specifications and look at this hardware, these are things that actually you can very much do within either end of this first year or when you start your second year itself. All right, because by the end of this first year, you have done a fair amount of prototyping, how to integrate systems together, how to put things together. You know about peripherals, you know about UART, you know about ADC, and so on. All right, and when you start your year two, you're going to be exposed to more advanced systems. You're going to be talking about multi-threading, this kind of microcontrollers, RTC, and so on. Okay, so what the TraceTogether system has is actually something that almost all of you can do. All right, it's nothing that complex or whatever. All right, the only part that is again that you probably are still not maybe not yet sure about is all those data encryption, all right, and security related features. Okay, so if you look at the document, okay, they have given us some background on the protocol, okay, how it communicates, okay, what kind of data it stores, and so on. Okay, so this document you can get it, or I can send to you as well, just to have a look. So it gives you the idea of how you can design systems that talk to each other. Correct. And we are going to be applying some similar concepts for our project. Okay, because in our project, okay, so let me come back here. In our project, what we will be doing is we have your RPi, okay, you have RPi, okay, and it's going to be talking to your Uno, okay, and your Uno is basically like what I drew the last time. This is going to communicate to your motors, all right, and then beside your motors, you are also going to have your input, which is your line encoder. So that is to give you feedback on how your wheels are turning. Okay, at the same time, okay, you are also going to be communicating to your RPi through the serial. Okay, so this is your UART interface. Okay, and your RPi is going to be connected to the LiDAR. Okay, in terms of relating this to your project, when your RPi talks to your Uno, there must be a way in which you communicate, because what is going to happen is your control and command is actually through the RPi. Okay, so over here, when you're using your keyboard, okay, to send commands to your RPi, you're going to send it some information. Okay, make the robot move right, make the robot move left, and so on. Okay, and that is going to be done wirelessly. Okay, so this is actually this is going to be done wirelessly. Okay, through Wi-Fi. Okay, so this is your computer. You're going to talk to the RPi wirelessly, and you're going to send some commands. So when you send some commands, your RPi must be able to interpret those commands, and your RPi must be able to send the correct command to the Uno. The Uno must be able to send some response back to the RPi. So there must be a protocol in place. All right, how do I send a particular data packet? Okay, so we're going to be learning about this kind of thing. Okay, so how do I structure the data packet? Okay, bits, this bits refer to what, this bits refer to what, and so on. And of course, things can also go wrong. Correct, in any data transmission, things can go wrong. While I'm transmitting the data, okay, I transmit this as one, but by the time the RPi receives it, the Wi-Fi network, something went wrong, the RPi receives it as 0. Correct, so when things go wrong, how do you deal with it? How do you react? Okay, so these are all the things that we are going to be learning. All right, and when you learn all these things, you can see that it encompasses a lot of different components of how you design a system. Okay, so it looks very complex, but again, we will be giving you a lot of helper functions and libraries to get you moving. Okay, so even though you have all of this to help you, the concepts that you're going to learn are very important, because now you can apply those same concepts to, let's say, if you were to come back to this TraceTogether and say you want to create devices that can talk to each other. Correct, and then you can say, okay, how do I design a protocol? What kind of hardware do I use? What kind of software do I implement, and so on. Okay, so this to give you some motivation. Okay, why all this is important, because as computer engineers, when you graduate, these are kind of things you are expected to be able to do. All right, in terms of hardware design or software design and things like that. All right, so that is basically uh, just to give you some idea. Along the way, I will also share other stuff that some of my other students have done in terms of projects or some other research work that they have been doing. Okay, and hopefully you have some idea of the things that you're able to do. All right, so yeah, so like I mentioned, in most cases the tutorial should be able to end within 1 hour. So now it's exactly 5. Okay, so that's all I have. Thank you very much, and I will see you all on Tuesday.